In this video, I'm going to talk about looking at associations between categorical variables using something called contingency analysis. And so to illustrate, we have some data here from an experiment that looked at a possible relationship between cancer and taking an aspirin. So let's take a look at the data here. And so this is called a contingency table, and it summarizes the results of this particular experiment. And so what happened here was we had 19,934 women that received 100 milligrams of aspirin every other day, and then we had 19,942 women who received a placebo. And then these women were all followed for 10 years, and then it was recorded whether or not they were diagnosed with invasive cancer in that time period. And so what this contingency table does is it breaks down the data and cross-classifies it. So for example, of the women who received the aspirin, 1,438 did go on to develop invasive cancer in that time period, whereas 18,496 of those women did not. And of the women that received the placebo, 1,427 developed invasive cancer, whereas 18,515 of them did not. And so it's always good to start off any statistical analysis by looking at a graph of the data, and in this case there's a graph called a Mosaic Plot that's particularly useful. And so what this graph does is it puts the two different treatment levels along the horizontal axis. So on the left hand side we've got the women who had the aspirin treatment, on the right hand side we've got the women who received the control treatment or the placebo, and then on the vertical axis we've got the bars colored and stacked according to whether the women did not develop cancer, which is the yellow bars, or if they did develop invasive cancer, which is the dark red bars there. And so what we can tell just by looking at this particular graph is it doesn't appear to have much of an impact on whether or not a woman goes on to develop cancer, whether they had an aspirin or a placebo. In this case, the red bar relative to the yellow bar, it's very similar for both treatment levels. So to quantify that finding, we're going to look at something called relative risk. And so what relative risk does is it looks at these numbers in the contingency table, and then it uses a particular formula to summarize the relationship between the numbers. And so let me run through that calculation. First of all, I'm going to think about the probability of someone who receives the aspirin going on to develop cancer. So there were 19,934 women who did receive the aspirin treatment, and 1,438 of them went on to develop cancer. So if we express that as a probability, we would have 1,438 divided by 19,934. And so the code that I'm going to use here is I'm going to pick off the two numbers that are relevant to this probability. And so A is this number here, 1,438, and the code that I'm using here, these numbers, the first number tells us what row in the table we're looking at, and the second number tells us what column. So first row, first column is this number. And then the other number that I'm interested in is this one. So in the table it's second row, first column. So that's this number here, second row, first column. And then if I calculate the relative proportion, we're going to have 1,438 divided by the sum of 1,438 plus 18,496, and that comes to 0.0721386. So there's roughly a 7.2% chance of the women in this study who were given the aspirin treatment going on to develop invasive cancer over a 10-year period. We can do a similar thing for the women who received the placebo treatment. So in this case, I want to pick off this number. So in the table, that was this number here in the first row and second column. So that was B, and then D is this number here. So second row, second column. So that's this piece of the code here. And then as a proportion, that's going to be 0.07155,752. So also roughly a 7.2% chance of developing cancer for the control group. So just comparing these two numbers, they're very similar, and we saw that in the Mosaic plot. That's why the relative size of the red bar to the yellow bar, or the sum of the red bar and the yellow bar, strictly speaking, was similar for both groups. And actually, if anything, it looks like taking an aspirin works against you in terms of your chance of developing cancer. This probability here within the aspirin group is actually a little bit higher than it is in the placebo group. So does that mean that necessarily that taking aspirin is a bad thing in terms of your cancer risk? Well, remember, we've just got a sample here, and we're trying to make an inference about a broader population from a sample, and so there's always going to be sampling uncertainty, and so we would need to quantify that uncertainty somehow to be able to ascertain whether taking aspirin really is dangerous in this case. And so one way to do that is to calculate a confidence interval. So if we think about the ratio of this number to this number, that's something called relative risk. So I've abbreviated that as RR. And so in this case, it comes to 1.008113. It's a number that's ever so slightly bigger than 1 because this probability in the aspirin group was ever so slightly higher than the probability in the placebo group. Okay, so that's why this relative risk is bigger than 1. If it was exactly equal to 1, there would be no difference between the two different treatment levels. If the relative risk is bigger than 1, then the probability of an adverse outcome in the treatment group is higher than the probability of an adverse outcome in the control group, and so that indicates that the treatment, which is aspirin in this case, is counter-effective. It's increasing our chance of an adverse outcome, which is presumably not what we want. And if the relative risk is a number less than 1, then that would indicate the probability of an adverse outcome is reduced for individuals who had the treatment, the aspirin in this case, and that would indicate that the treatment is effective. And so what we would like to do is come up with a confidence interval that we can use to express our uncertainty about likely values of the relative risk in the population. And so that's what we're going to do here in this calculation. So it's a little bit complicated here because we actually have to figure out a confidence interval for the log relative risk and then exponentiate our endpoints to get a confidence interval for our relative risk. So first step is to calculate the standard error for the log relative risk, which is given by this formula. So as a number, that comes to this number here. Next, calculate a critical value from a normal distribution. For a 95% confidence interval, we're going to use the 97.5th percentile, which is a number that everybody should know by this point in time, 1.96. And then we can calculate the lower bound of the confidence interval for the log relative risk. That's this number here. But if we exponentiate that number, we get the lower bound for the confidence interval for the relative risk. So that comes to 0.9394365. If I round that off to 2 decimal places, we get 0.94. And then similarly, here's the upper bound for the log relative risk. And if I exponentiate it, I get the upper bound for the relative risk. So 1.08181, or if I round that to 2 decimal places, 1.08. So we're 95% confident that the relative risk in the population is between 0.94 and 1.08. In particular, we can't really rule out a relative risk of 1, because 1 it's inside that interval. Okay, so what that tells us is that this experiment cannot rule out the possibility that the relative risk of developing cancer for aspirin users relative to people not using aspirin, we cannot rule out the possibility that that relative risk is equal to 1. In other words, no effect. So that's how to calculate this confidence interval by hand. We can actually skip all of these calculations using this function here. And this function is available in the EpiTools package. So if I run this piece of code here, that's going to install and attach the EpiTools package, and then that allows me to use this function. We can have a look at the details for the function here. So that tells us what it's going to do, estimate the risk ratio and also a confidence interval. And so in this case, if I run this code here, so I'll invite you in your own time to look at what these two arguments are doing. So all the details, as usual, are down here, so you can read what rev is referring to and then what method is being referred to. And then in the output down here under value, it tells us that one part of the output is called measure, and that gives us the risk ratio and the confidence interval. So if I pull off a particular part of that piece of output, I get there's the estimated relative risk. So that was the number that we calculated before by hand. And then this is the lower bound of the 95% confidence interval. We calculated that by hand here, and here's the upper bound of that 95% confidence interval, and again we calculated that by hand here. So once you're comfortable with the idea of what relative risk is measuring and how the formula for the confidence interval works, then you can go ahead and just start using this formula to get the values directly without having to do all these hand calculations here. Okay, so that's how to calculate relative risk and confidence interval for the relative risk for a 2x2 contingency table.